All right, we're going to continue on. We're now going to do something very similar to what we just did with the position function. Because we haven't used the fact just yet that the change in distance was 264 feet as velocity went from 45 to 35 to 30 miles per hour at a constant rate of deceleration. But we do know that by the fundamental theorem that the integral from 0 to a of v of t dt is the antiderivative of velocity, which is position evaluated at the upper limit minus the antiderivative of velocity evaluated at the lower limit. So S of a gives us 1/2 k a squared plus 66a. And since we're told that, or we're given that S of 0 is equal to 0, the position at time t equals 0 is 0, we can now state that 1/2 k a squared plus 66a is equal to 264. We still have two variables, but that's why we solve for k in the preceding problem. So substituting for k equal to negative 22 over a, we get 1/2 times negative 22 over a times a squared plus 66a is equal to 264. And since negative 11a plus 66a is 264, so 55a is 264. And so a is equal to 264 over 55, which is equal to 4.8, which we can now plug back in for a in the diagram. Okay, from this point we basically want to find out what that the change in time is from 4.8 to the end. And I'm going to call that x. And I would imagine there's some way of going about doing this using an integral, but you can see how much work it was just to get to this point, and it would be so much easier to use similar triangles at this point. To get the proportion x is to 44, that's the base of the small triangle to the height of the small triangle, is the same as x plus 4.8, which is the base of the large triangle, is to 66 over 66. Multiplying that out and simplifying that, we're going to get x is equal to 9.6. Now at that point you could change b or rewrite b as 4.8 plus 9.6, so that b, time at b is 14.4 seconds, and we could do a simple integration to do the integral from 4.8 seconds to 14.4 seconds of v of t dt, and that would give us the area under there. But it's so much easier at this point to just do this using a triangle formula. So the base is 9.6, the height is 44 divided by 2, and that comes out to be 211.2 feet. And that is the distance that the car travels while decelerating from 44 feet per second down to 0 feet per second. Now, my point in doing this is that certainly I believe that just using geometric formulas was the easier way to do this problem, and probably that's what they had in mind at the beginning. But hopefully you've learned something from the integration that I did, at least in the first few steps of that, to get the time at which the vehicle was traveling 44 feet per second. Because we will use that type of integration again and again, and hopefully you got something out of that. And if you need, follow it again and again, and listen to it again and again, and hopefully you'll pick up some important things from that. But this problem could have been solved purely using geometric formulas, and may have been much simpler to do it that way, in which case normally that's fine. There's no reason why you couldn't do it this way on an AP test or on any test. Okay, hopefully that helps.